Hello guys, so this is our review for the subject MEE012 which is heat transfer. So before we start this review, tingnan natin yung mga subject na i-discuss natin within this review material. Okay, so first topic that we will be discuss is some background about the heat transfer. Second will be about conduction. Third is the conduction through a plane wall. Fourth is conduction through a composite walls. And then the fifth one is the conduction from fluid to fluid. So that will be the focus of our topic for today. So konting reminders lang if you are looking for a detailed topic or a detailed discussion about this topics, then this is not the right video for you. But if you are reviewing or you are preparing for an examination or for a quiz, then this is the right video for you. Okay, so let's start this discussion by defining what is heat transfer. Okay, from definition, heat transfer is the movement of heat from one body to another by means of conduction, convection, or radiation. Okay, so ang ating heat transfer, meron tayong three modes of heat transfer. First is the conduction, and then the definition said that conduction is a mode of heat transfer in which heat is transferred by molecular interaction through bodies in contact. Second mode is the convection, which is a mode of heat transfer in which heat is transferred due to the mixing and motion of particles of a substance. And the third mode of heat transfer is the radiation, which is a mode of heat transfer in which heat is transferred between bodies by energy propagating electromagnetic waves. Okay, so for the part one of our review material, we will be focusing on conduction itself. Okay, so this convection and radiation will be discussed on the next part of our review. But for the meantime, let's go to conduction. For the conduction, this is the common formula that you need to be familiar with, or ito yung formula na ginagamit natin when solving your conduction problem. Okay, so we have here your Q is equal to your U A delta T, where your U is your overall conductance, Q is your heat transmitted, your A is the heat transfer area, your delta T is the temperature difference between the 2 points, which is equal to your T high and T low, or temperature in the high point and the temperature in the cold point. And then we have here your TH, which is the temperature on hot side. TC is the temperature on the cold side. Okay, so we can also rewrite this equation. Instead of using your overall conductance, we can solve for the heat transmitted using the overall resistance, where your Q is equal to your A delta T over RT, where your R sub T is the overall resistance of your wall or of your conduction. And then here we can see that your RT is actually the reciprocal of your U. So the overall resistance is actually equal to the reciprocal of your overall conductance. So this is the common formula or the basic formula that is used in heat transfer. And then let's have an example for this. So example, we have here an heat exchanger has an overall coefficient of heat transfer of 0.5 kilowatt per meter squared Kelvin. And the heat loss is 11 kilowatt and the mean temperature difference is 15 degrees Celsius. So what will be the heat transfer area in per area in feet or the heat transfer area in feet squared? So right now we are finding or we are looking for the area or the heat transfer area A, okay, for this equation. And then from our formula a while ago, we have here the formula Q is equal to your U A delta T, where your Q is equal to 11 kilowatt, that is the heat loss or the heat transferred. Your overall conductance, coefficient of heat transfer, is equal to 0.5 kilowatt meter squared Kelvin. And your E is unknown, and your delta T is equal to 15 degrees Celsius. So mind you, your 15 degrees Celsius is actually the temperature difference. So what is the difference between the temperature and the temperature difference? Kapag we are tackling about temperature, that is the measure itself. But when it comes to temperature difference, that is the difference between two temperatures. So don't be confused between the temperature and the temperature difference. So just like this, diba, ang nagiging difference lang niya is when we are solving and when we are converting from one temperature scale to another, maiba yung formula na nagagamit or there is a difference between if you convert your temperature to your temperature difference. So for example here, for this, we know that your Q is equal to 11 kilowatt, your U is equal to 0.5 kilowatt per meter squared Kelvin, A is unknown, and your temperature difference is 15 degrees Celsius. if you can see, we need to make your units common with each other, or we need to make the units the same so that we can cancel it out. So in here we have degrees Celsius, but in the overall coefficient we have the Kelvin. So we need to convert this temperature difference into Kelvin. Okay, so most of us will think that this 15 degrees Celsius will be converted by adding 273 so that it will be Kelvin. But mind you, or I'm reminding you that this is not a temperature, that 15 degrees Celsius, but it is a temperature difference. Okay, so let's see the analysis of here of this. So converting your 15 degrees Celsius temperature difference. Okay, so your temperature difference is actually equal to 15 degrees Celsius, or it is also equal to 15 Kelvin. So how come that your temperature difference, which is 15 degrees Celsius, is equal to your 15 degree Kelvin? Why not add 273 here? Okay, so this is the explanation here. Your delta T is actually equal to your T high minus your T hot minus your T cold, as I have said earlier. And then if we will be using ano, value here, which is on Celsius, your temperature difference is the Celsius of high minus your Celsius low, cold. And then if you will be converting it into absolute Kelvin, because according to the when you are solving problems under thermodynamics, we are being reminded that we always need to use the absolute value for temperature and pressure. So if we will convert your Celsius high or Celsius hot, you will add 273, and then if you will convert the cold temperature, you will also add 273. If you will be simplifying this, you will be distributing the negative sign or the negative one here. That will become the hot temperature minus your cold temperature plus 273 minus 273. So notice here that your plus 273 is subtracted to minus 2, negative 273. And then that therefore your 273 minus 273 is equal to 0. That's why when you are solving for temperature difference, okay, your Celsius hot minus your Celsius cold is actually equal to your Kelvin hot minus Kelvin cold. So it is safe to say, or we can say that your change in temperature is, which is 15 degrees Celsius, is actually equal to your 15 Kelvin. Okay, so that is the difference between temperature and temperature difference. So always take note if there is a term temperature difference or if the term is temperature. Okay, so more on that, let's solve. So since we know that your 15 degrees Celsius can be converted into 15 Kelvin, we have your 11 kilowatt is equal to 0.5 kilowatt per meter squared Kelvin, A multiplied by your 15 Kelvin. And then right now we are finding your A. So your A is actually equal to your 11 kilowatt over your 0.5 kilowatt meter squared Kelvin multiplied by 15 Kelvin. So we will be having your unit analysis. Your kilowatt will be canceled out here. Kelvin will cancel out. So the remaining unit will be in meter squared. And the answer is 1.467 meter squared, or 1.467 square meter. Okay, and then the question says that we need to find the heat transfer area in feet squared. So we will be converting your 1.467 meters squared into feet. So in 1 meter, there is 3.281 feet. So squared it, since it is squared here. So meter squared will cancel out. So the unit will be in feet squared. And the answer will be 15.79 meters squared. Okay, so that is for your conduction. Okay, next topic, we have here the conduction through a plane wall. And then, assuming that we have here a plane wall here, this is your wall. And then, we have the hot temperature here. Siyempre, meron tayong hot temperature dito. Dito yung cold temperature mo. And then, we will be having a heat transfer from through the wall. And then we have a thickness of the wall here, which is denoted as x. Okay, so for the for the basic formula that is used on your conduction through a plane wall, we have your Q is equal to A delta T over R. We have this formula from a while ago, where R is your resistance. And then since we have one resistance here, which is the wall, the resistance is actually equal to your X over K, or the thickness over the thermal conductivity K, where your K is your thermal conductivity with a common, or with the unit, or the common unit is in watt per meter Kelvin. And then we have here your delta T, which is your T high minus T cold for this. Okay, and X is your thickness, by the way. So if you will be getting the formula for your conduction through a plane wall, your Q is actually equal to your A multiplied quantity TH minus Tc over your x over k. So this is our working formula for conduction through plane wall. So let's have an example here. So assuming that we have a 15 centimeter thick wall, so this is the thickness of the wall, which has a thermal conductivity of 5 watt per meter Kelvin. This is thermal conductivity K. If the inside and the outside surface temperature of the wall are 230 degrees Celsius, so this is the hot temperature and this is the cold temperature or the temperature on the cold side. And then we need to determine the heat transmitter. So we are finding your Q. Okay, so your Q is actually equal to your A, TH minus TC over X over K from our formula a while ago. And then since I know the area is not given, the area here or the surface area of this wall on this side is not given. So we will be getting the Q over A instead. Your Q over A is equal to TH minus T cold over X over K. Okay, where your T hot minus T cold is equal to your 200 minus your 30. And then just like what we have said earlier, if you add 273 here and then you add 273 here, you will just cancel it out. So 273 minus 273 is ano, 0. So it is safe to say that we will be making your degree Celsius 2 Kelvin here. Okay, so your 200 minus 30 Kelvin, that is your change in temperature. And then your thickness is 15 centimeters. So that, we will make the unit common or the same with each other. So we will be converting our centimeter into meter. So there are 100 centimeter per meter. Convert this will become 0.15 meter for our thickness. And for the thermal conductivity, we have 5 watt per meter Kelvin. Okay, so let's start. Let's solve this. So your QA is equal to 200 minus 30 Kelvin. This is your TH minus TC. Your X is 0.15 meter, and then your K is 5 watt per meter Kelvin. And then if you'll be having the unit analysis, the meter will cancel out here. No. Your Kelvin will cancel out, and then this meter will become meter squared. Watt will be on the upper side. So this will become watt per meter squared, is in your unit analysis. And then the final answer will be 5,666.67 watt per meter squared. And then right now we can convert this into kilowatt. And then we know that there is 1,000 watt per kilowatt. So this will become 5.6667 kilowatt per meter squared. So this is the final answer for this problem for conduction through a plane wall. Okay, next topic, we have your conduction through composite plane wall and the working formula for your conduction through composite plane wall. Let's derive this. So from our first formula a while ago, your Q is equal to A delta T over the resistance. And then for the conduction through composite wall, since we have multiple resistance here, as you can see, we have two walls here. Okay, for this figure, we have two walls. So there are two thermal conductivity, assuming that there is different material on the wall. And then we have thickness for each wall. And then we will be having that temperature here. We have temperature in this side and temperature for this side. And then we will be having the Q here or the heat transfer on the wall or on the composite wall. So since we have multiple wall here, it is your RT or your total resistance is actually equal to the summation of your X over K. So if we will be having the summation of this, since this is 2, so your summation, your RT or your total resistance is actually equal to X1 over K1 plus X2 over K2. So this is we only have two walls, so this 2 is enough for this figure. But if there are more walls here, so you can add and so on and so forth. But the resistance is actually X over K, depending on the number of walls. Okay, and where your K is your thermal conductivity, X is your thickness, and then your delta T is your T hot minus T cold. Or this is the T hot, this is the T cold, if you will be considering two walls. Okay, so from this, you will have your Q is equal to your area over T hot minus T cold over the summation of your X over K. And then this is the working formula for your conduction through composite wall. So remind you, the heat transfer through these two walls is actually equal to the heat transfer on your wall 1 here. And it is also equal to the heat transfer on your wall 2. So again, your heat transfer on these two walls is actually equal to the heat transfer on your wall 1 and it is also equal to the heat transfer in your wall 2. So your Q is actually equal to Q1 is equal to Q2 is equal to Q3. You can equate that. So from here, from the composite wall, we have this formula. Okay, your A is equal to T high minus T cold over the summation of your X over K. And then for your wall 1 here, if you will consider this wall 1, so your Q1 is equal to A T1 minus T2 over your X1 over K1. And then for your wall 2, if you'll be considering wall 2, that is your area T2 minus T3 over X2 over K2. So you can equate actually this equation so that if one is unknown or if you want to get something from the value of each other or it just says equal yung heat transfer mo on this two walls equal siya sa heat transfer with your wall 1 and equal din siya sa heat transfer with your wall 2. Okay, so we will be having an example for this for the conduction to composite wall. So example that we have two walls of cold storage plant which are composed of an insulating material which has a thermal conductivity of 0.25 kilojoule per hour meter degree Celsius and 100 millimeter thick. And on the outer layer, there is another material which is a 3.5 kilojoule per hour meter degree Celsius thermal conductivity in a 15 centimeter thick. Okay, so if the surface temperature of the cold side is 30 degrees Celsius, that is the cold side. For the hot side, we have 250 degrees Celsius. So we will be finding the heat transfer per square meter or the heat Q over A or the heat over area. So from our formula for the conduction of composite wall, we have your Q is equal to A TH minus TC over the summation of X over K. So finding your Q over A, that is TH minus TC over, and since we have two walls here, okay, so for the wall 1, the resistance is X1 over K1. For the wall 2, we have X2 over K2. Okay, solving for your X or making your units the same or uniform with each other, we will be converting our 15 centimeter into meter. So there are 100 centimeter per meter. So your X1 is actually equal to 0.15 meter. And then for the thickness of your wall 2 here, that is 15, wall 2 here, that is, I guess the illustration is wrong. That is here. That is 100 millimeter. So your 1 meter is actually equal to 1,000 millimeter, and then therefore your x2 or this part is 0.1 meter. Okay, so solving that, moving forward, your Q over A is equal to your hot side temperature, which is 250 degrees Celsius, minus the cold side, which is 30 degrees Celsius, over your X sub 1. Your X sub 1 is 0.15 meter, and then for a 0.15 meter thick, your K is 3.5 kilojoule r meter degree Celsius. And then we have the 0.1 meter thick wall. And then the 0.1 meter thick wall has a thermal conductivity of 0.25 kilojoule r meter degree Celsius. And then if we will be solving that, you will get the Q over A, which is 496.77 kilojoule per hour meter squared. So we can convert this kilojoule r into kilowatt. So in 1 hour, there are 3,600 seconds, and in 1 kilowatt, or is equal to your 1 kilojoule per second. So cancel out your kilojoule here. Second will cancel out. Your R will cancel out. So the remaining will be in kilowatt meter squared. So your answer will be 0.138 kilowatt per meter squared. So this is your Q over A for this problem. Okay, next we have here the conduction from fluid to fluid. So for conduction to fluid, as you can see, we have here, this is combined now with your conduction through composite wall. We have walls here, 3 walls. And then if you can see, we have here some fluid. Maybe this is steam, or on the other side, maybe this is air. But as you can see, we have here conduction from fluid to fluid. This is your temperature hot. This is temperature cold. We have your temperature here at the side of your T1, your T2, your T3, and your T4. Okay, so this is your conduction, and the thickness of your walls is here, thermal conductivity, and then your fluid here has a surface film conductance 1 and surface film conductance 2. Okay, so for fluid conduction from fluid to fluid, your total resistance is actually equal to the summation of your 1 over h, or that is 1 over h1. H1 is the surface film conductance of the fluid, which has a unit of watt per meter squared Kelvin, plus your 1 over h2 and so on and so forth. Okay, so if we will be putting it here on this equation, your Q is actually equal to A TH minus TC over the summation of 1 over H. Okay, if we will be combining this with your composite wall formula, so your Q is equal to A delta T over your RT, where your RT is equal to the summation of X over K plus the summation of 1 over H. This is the resistance from the wall, and this is the resistance from your fluid. So the working equation, if you will combine your conduction from walls to conduction from fluid, is equal to Q is equal to A TH minus TC, summation of your XK plus the summation of your 1 over H. Okay, so let's have an example here. So we have here a heat exchanger is to be designed for the following specification. Hot gas temperature TH is 1145 degrees Celsius. You have the TC, which is 45 degrees Celsius. The H1, or the unit surface conductance of your hot side, is 230 watt per meter squared Kelvin. For the cold side, or your HO, that is 290 watt meter squared Kelvin. Your thermal conductivity of the metal, or this wall, or this surface, is 115 watt per meter Kelvin. So find the maximum thickness of the metal, or we are finding the thickness of this metal wall between the hot gas and the cold gas, so that the maximum temperature of the wall does not exceed 545. Okay, so it says that the temperature at the wall, or the sides of the wall, must not exceed, or the maximum temperature is 545 degrees Celsius. So since this is your hot side, T1, which is 1145 degrees Celsius, therefore your temperature in this point, okay, or in this side of, or in this surface of the wall, must not exceed 545 degrees Celsius. So we will be having this as 545 degrees Celsius. So that is the maximum. So your T1 is 545 degrees Celsius. And then we will be finding your X here. This is your conduction. Okay. So first, we cannot solve this. In order to solve this, we need to find the Q first, or the resistance. So we could not solve for your total resistance because we have an unknown X here. If we will be solving that, we have two unknowns, your X and your Q. So we could not solve that. So we need to find another formula. So we will be finding the conduction from this fluid, this hot gas. We will be finding the conduction in the hot gas, and that is actually equal to your area. Your Q is equal to your area, Ti minus To. This is your Ti, and then this is your T1. This is your T1. Ti is 1145, T1 is 545. We will be having the conduction between these points, and then the only resistance is the fluid. So that is 1 over H1. This is the resistance, total resistance for your fluid. We are considering this part, okay, this side only, from Ti to your To. Okay, so from I to O, we know that your T1 must not exceed 545 degrees Celsius according to the condition here. Therefore, your Q is equal to A Ti minus T1 over 1 over H1. Okay, and then getting the Q over A, since area is not given, your H, it is actually equal to your H1 Ti minus T1. So your QA is equal to your H1, or the unit surface conductance for the hot side, is 230 watt per meter squared Kelvin. Your Ti is 1145, and then your T1 is 545 Kelvin. So Kelvin will cancel out. The remaining will be in watt meter squared, and that is equal to 138,000 watt per meter squared. So that is your Q over A. And take note, as I have said earlier, your thermal heat transfer here is equal to the heat transfer in this part. It is also equal to the heat transfer here, and it is also equal to your heat transfer on ano, the whole. Okay, for the whole figure. Okay, so we can equate this in since we have your Q over A, we can already equate this considering the whole setup. Okay, so moving on for the problem from I to O, so we will be considering the heat transfer from I to the cold side O. This is the cold side part. Okay, so your from I to O, we have a total of three resistance. First is your resistance in this fluid. Okay, another is your resistance in this wall, and the third resistance is your resistance in this fluid again. So from your formula a while ago, your Q is actually equal to your area TH minus TC over the summation of your XK over the summation of I plus the summation of your 1 over H. So for this setup, we have three resistance. So that is your Q over A is actually equal to your Ti minus To. This is your Ti. This is your To. And then the first resistance is this hot gas, that is 1 over H1, and then this wall, that is X over K, plus the resistance here, which is 1 over H2. Okay, so we already got the value of your Q over A, which is 138,000 watt per meter squared. And then over your inside, or the hot side, is 1145 minus your O, which is TO, which is 45. That is the change in temperature. And then your 1 over H1, your H1 is 230 watt per meter squared Kelvin given a while ago. And then your X, okay, your thermal conductivity is 115 watt per meter Kelvin. Okay, your X is unknown, the thickness, and then 1 over your 291 per meter squared Kelvin. That is the unit surface conductance for your cold side. Okay, so solving for your x, you will be getting the value of your x, which is 0.020115 meter. If we will be converting this into millimeter, there are 1000 millimeter per meter, so that is equivalent to 20.115 millimeter. And that is the thickness of your wall here, the metal wall here. Okay, so that's all for the review of our MEE012 heat transfer. We have reviewed the heat transfer, conduction, conduction to plane, wall, conduction to composite plane walls, conduction from fluid to fluid. We have discussed or we have familiarized the formula that is commonly used, and then the common terms that we could encounter during the quiz or the examination. Also the concepts or the things that we need to put in mind. So I will be posting this PDF or this review materials on the Google Classroom, and then I hope that you will pass your examination and your quizzes. So I thank you for watching this video, and bye guys.